Okay, good morning. So let's continue our discussion on the planar robot uh, uh, forward kinematics, inverse kinematics, and control. So last meeting, we had a visiting lecturer, and he helped me in terms of showing you the basics of robot control, the basics of defining motion in 2D space as well as in 3D space. And so we mentioned that the, the control in 3D space is much more complicated. And so we need to concentrate first in the 2D space. So that's why we come out with a very simple example, excuse me, of a 1 degree of freedom robot, which we have shown here. And so we say that the 1 degree of freedom robot from flat going up, and this is the angle that the robot moves for the 1 degree of freedom rotational joint on the plane. So this is the x-axis and the y-axis. It's lying on the table, and then it just moves its arm like this. It sweeps on the table. Okay, from 0 degrees up to, I think this is 60 degrees. Okay, so we call it elbow, or around 55 degrees. And so we call it elbow. And so this elbow moves from, given the time, this is your axis. In this case, this is the horizontal axis time, and this angle, and it goes up to around 60 degrees. So from 0 up to around 60 degrees. So the angle will go from 0 up to around 60 degrees given time. Okay, so that's how it is going. And so you can see that the angles are not really linear. So it goes these are the increments of the angle, and then it goes almost like linear, and then suddenly it becomes smaller and smaller and smaller. And so you see here, the line is almost linear, and suddenly it flattens a little bit and becomes flat. Okay, so that's how it is plotted in this linear axis. So now we also plot the hand. Okay, where is the hand with respect to the world? So the hand, this is the hand or the end effector or the tip of the robot. And so this is the X hand, and then the location of the hand with respect to the X-axis, and the other one is the location of the hand with respect to the Y-axis as the robot moves from here to the 60-degree angle. Okay, so we plot the position of the hand. So this hand goes with respect to the X, it goes from here to around 0.45, and then moves a little bit, moves inward until it reaches here. So that's the hand axis. So from 45, it slowly goes, the value along the x-axis is getting smaller and smaller. Okay, so that's why the plot is here. And then for the y-axis, it's from 0 to a higher value. Okay, again, this is the separate, the points are like almost linear and becomes smaller and smaller in terms of the interval. So here, from almost linear, suddenly it flattens and then becomes this one. Okay, so this is the plot of the hand hx, h with respect to the x-axis, and h with respect to the y-axis, or the hand with respect to the x and the hand with respect to the y. So what I want you to understand is that when you plot with respect to the joint, the joint space or the configuration space, it is normally based on the axis of the angle. It is based on the axis of the joint angles. And then when you plot with respect to the world frame or the world coordinates, then it is based with respect to the x, y, and z coordinates of the world space. Okay, and so in this case here, we're just considering position of the hand, and so we're not considering the orientation. So we only see the x, y, and z position. In this case, x and y position of the hand. Okay, so we call this information. We call this the direct computation by inputting the joint and then seeing what happens to the hand, computing the hand axis as the forward kinematics. Okay, forward kinematics, we say that here we have mentioned forward kinematics where we compute the joint for this 2 degrees of freedom robot. You compute the resulting x of the hand, the x value of the hand, and the y value of the hand by computing the length link 1 axis multiplied by cosine theta, which is this part. Okay, this part. Okay, this is the first part, this one, and then this part. Okay, cosine of theta 1 and theta 2. Why theta 1 and theta 2? Well, it's because from the horizontal axis, this is the horizontal axis, goes from theta 1. So I'm from the horizontal axis up to theta 1, that's theta 1. Okay, and you can see theta 1 is added to theta 2 to get your total angle of length 2. Sorry, the internet got disconnected. Let me share again. Okay. So do you understand that part? We're just computing only the forward kinematics. So when we say forward kinematics, again, you input the joint angles, input theta 1, input theta 1, and then input theta 2. Okay, and then you compute the output is the hand x-axis and the hand y-axis, which is the hand is this. Okay, so now let's consider first this part. That part is this part. Okay, L1 multiplied by the cosine of theta. That is this part. Okay, and well, this other part is L2. Only this one L2. Hello, good morning, Miss Shaw. Sorry, I'm having a class. Yes. Yes. Around 2 o'clock. Around 2 o'clock. Yes. Okay, thank you. Thank you, Prof. Okay, you're welcome. Okay, now this theta 1 and this is theta 2. I mean, this is theta 1 because this axis is the horizontal axis. And now it goes to that axis where this axis is supposed to be where theta 2 originated. Okay, it was flat like that. Just like here, okay, if you see theta 1, I mean the joint link 1 started like that. And link 2 also started like that. So when link 1 goes up, so it will have link 1 going up here, and link 2 went up with it. Okay, so that is joint 1, and then now joint 2 goes here, and so you have another angle of joint 2. So joint 2 move from here to there, and so the total angle that joint 2 moves with respect to this original axis is theta 1 plus theta 2. So that's why you have theta 1 plus theta 2. Okay, hold on. Theta 1 plus theta 2. So this length, cosine, is that length. And that length, cosine, is this length. And you add them together to get the total of the x-axis. Okay, you have a question, Itumele?
Yes, sir. I was asking, with the increase of links, we keep adding the L1, L2, and then keep increasing the number of thetas that are in each bracket going forward, right? Just to confirm that.
Yeah, I mean, you do that because I mean that is the geometric interpretation. Yes, it doesn't mean. I mean, well, it just so happens because the links are connected by rotational joints and they're on the plane, and so yes, the answer is yes. But okay, you should not memorize it. I mean, it's just a consequence of the configuration of the joints. Yeah.
Thank you, sir.
So if you keep on adding a link like this, yes, that's true. Then another link here. So you just keep on adding the length and the total angles. Because the answer to that is because physically it is what happens. So again, for example, this link will move with respect to this original length. So there's an angle there. Okay, and there's another angle here. Okay, and then additional angle there. It's just like that. Okay, so yes, you keep on adding it. Okay, so now, okay, I guess you understood that one already. I just want to emphasize. So with respect to the y coordinate, to the y component, so this is the length of link one, and then the sine of the y component, so this part, and again the total joint angles, the sine of it is that part, and so when you add it, the sine of it is this part, and then you add it, that's the total y coordinate. Okay, so you just add component by component. This part is that part, and this part was that part. Any questions? Yeah. Was this part?
Sir,
Yes.
assuming that according to how Itumeleng asked you, the links that you gave as an example are moving in an anti-clockwise manner.
Are moving
Assuming the
what?
third link,
Moving in the what?
the third link that you just added as an example,
Mhm.
and the others that followed it, you have added them in an anti-clockwise manner, right?
Yes.
Assuming the third link goes in a clockwise manner,
Mhm.
are we still going to
Add them.
add
Yes.
that particular angle, or we subtract?
You add them, but the sign of that angle changed, so it's just adding a negative angle. It's just a measurement.
Okay, which means we're
Mhm.
okay.
The feedback in the angle will change as you move in the other, as the angle goes in the other direction.
Okay.
So in the program, this is a corone. Okay, in the program, you don't need to change anything in the program. You just add everything, because the feedback of the joints will give you the corresponding sign. Okay, so the equations doesn't change. The equations don't change. Understand? Okay. I guess your questions tell me that you understood this part. Okay. So let's go to the third part. It's the same. Yeah, this is what you keep on asking. So now you have this. Okay, again, we add and just let me go through the motion so that I can emphasize. So that's L1 cosine of theta, and then you have theta 1 and theta 2. Okay, and so that is that component you add. Okay, so that component is added here, and so now you see here, just be careful, that's theta 2, and theta 2 was here, which is parallel to this, and then the horizontal line like that. So this is theta 1, and then that is theta 2. Okay, that's theta 1, theta 2, and theta 3. So now you have three angles added together. So that's why this one, and so that part here, this part, the component along this, maybe I'll make it a different, this part, okay, is that part, this whole thing. Okay, so the same thing in terms with respect to the y-axis. So here, that is this component. So again, this is just component by component all the way. Okay, because you are decomposing each components according to the corresponding axis. So L1, the L2 times sine. So this part here is that, okay, and L3 times sine of the total angle. So we know already the total angle is that, okay, and the sine is that part. So that part. From here, remember this is important, from here up to there, okay? Okay, it is not from the down there, but from here up to there. So that's why you add that component, okay? So that means you added this one length, and then you added another length, and you added another length, okay? And so that's the total length from down here up to the top, and from down here up to the side, okay? Which is, in this case, that is the X component total. And in this case, that is the Y component in total. Okay, so don't worry about the signs. The equations will remain the same. The same thing in the 3D space. Everything, the signs of the angles will change accordingly depending on where you are located with respect to the zero of the joint, angle. Go in the clockwise direction, it will be positive, and go in counterclockwise direction, it will be negative. Okay, so again, I want to emphasize that this is done with respect to the one that we mentioned here is forward kinematics. You input the joints, you output the hand coordinates. Okay, that will be our exercise for the first, for the second lab session. Okay, so you change the joint angles, and then you just plot. Again, you just plot what are the joints, and then you plot based on those corresponding joint values, what will be the hand position with respect to X and Y for planar robots. Okay, that's very easy. But,
I have a question, sir.
yes, you have a question.
When we know the positions of the robotic arm, is it relative to the, do we know, is it the joint or at the end of the hand if it's a robotic hand?
Okay.
Like which coordinates is it?
Yeah, it is when you're talking about the hand, this hand, yeah. Okay, you're talking about what is the position of that hand with respect to what? Yeah, and so well, it is the addition of the total length. Okay, for example, the x-axis, it is from here to there. Okay. Okay, plus here to there, plus here to there. Okay, if you add them together, you bring it down here, so there's that length, and you bring it down here, there's this length. Okay, so this is the hand position with respect to the x-axis.
X-axis.
Yeah, so the x-axis meaning it is from zero, from the origin up to there. So that means the same as with respect to the y, from zero, because you're just adding length. Okay, length, you add that length, and you add another length. So it is from zero up to where the hand is. I mean, geometrically, you can interpret it that you can see it geometrically, but mathematically, it is also that same interpretation. It is based with respect to the base frame. So now that is what we really want. So all these computations, all these hand computation, it is normally based on the base of the robot. It will, with respect, it is normally with respect to the base of the robot. So the hand moving with respect to the base, where sometimes in our hand it is with respect to the shoulders, but in the robot it is with respect to the base of the robot. Where is that hand with respect to here? And so that's why the robot will move like that, you know, check these or these. Normally it is with respect to the base of the robot. Okay.
Okay.
Any other question? Okay, no more questions. So let's, I guess this is well understood. And then we move, this was the example that we did. And so we say that this is how they are being plotted for the 1 degree of freedom robot. And for the 2 degrees of freedom, then we just incrementally change the joint angle. So joint 1, in this case, this is, we change now the coordinate of the axis. Last time we have time element, now we change it. So this is theta 1 axis, and the other one is theta 2 axis. Okay, so we just plot them. We make theta 1 0, that means this was flat. And then we sweep theta 2. Theta 2 goes up like that. Okay, so theta 1 0, theta 2 will go up. Okay, the same thing as the first, as the single degree of freedom joint. Now you have 2 degrees of freedom, so we increment theta 1 a little bit, and then from there we sweep another sweeping like that. Okay, and then increase a little bit, and then we sweep again like that. Okay, and so on. Okay, and so on. It will be in your exercise, you will see it on your own, so that when you do the lab exercise, you can understand it, what's going on. Okay, so normally when you say joint space, normally it is the axes are with respect to joint 1 and joint 2. In this case, you just see joints. Okay, you don't physically imagine what's going on. Okay, but just values of joints. But in this case, the hand position and the hand position X is the one axis, and hand position Y is the other axis, and so you can actually see it just like how it is moving in the actual world space. Okay, because that is what you see in the physical world. This one, you don't see it in the physical world. This is just internal into the joints. Okay, but what we see is the movement of this. I mean, we can see the movement of the joints, but joint 1 respect to joint 2, that's very hard for us to see, okay, or to imagine physically. But here, in this case, the movement of the joints here with respect to the world, the X and Y coordinate of the world is the same as X and Y coordinate of the hand, and also the same as how you see this physical robot. And so that's why you can plot it like this. Okay. So again, this is forward kinematics. Given the joints, these are inputs, and output are the joint hand coordinates. Okay. Any questions with that one? So if we increase the size, hold on, excuse me. Do we have, I think no. So the question is, what happens if we increase the size? Well, okay, let's just clear everything. So now if we increase the size, we still have the same thing. We still have the joint space and the hand space. So what will happen is that when you have 3 joints, so you have theta 1, theta 2, and theta 3. So, okay, so this will be your theta 1. This will be your theta 2. Now it becomes a 3D space, and then theta 3. Okay, and then you can change the, okay, theta 1 like that, theta 2 will be this, and theta 3 will be that. That's the point, the first plot. Then maybe you can plot another point, theta 2 here, theta 1 here, and then theta 3 here. Okay, like that. Yeah, these are points. So these are points in the 3D space. And then now you will also plot with respect to the hand coordinates. So now it becomes X, Y, and Z of the world. So X, Y, and Z of the world. Okay. So in that case now, your hand, okay, well, because it looks physically, like it will look like the physical world. So you can just plot the hand in 3-dimensional space, for example, like that. Okay, this is your first joint. I mean, first hand position. Maybe the hand moves here. Then somehow the hand moves here also, like that. Okay, depending on the coordinates of the joints. Okay. So again, the input of the joints, of the joint values, will result into hand positions. In this case, joint values of theta 1, theta 2, theta 3, it will result into X, Y, and Z of the hand. Okay. Any questions? Well, sir, what if you increase the size? You increase some more. Yeah, it becomes 4 degrees of freedom. Yeah, 4 degrees of freedom or 4 joints. Well, it will be a 4 dimensional space in terms of theta 1, theta 2, theta 3, and theta 4. Then it will be hard for us to imagine. Okay, but then to imagine that, you can just take 3 at a time. So theta 1, theta 2, theta 3, and then theta 2, theta 3, theta 4, like that, or theta 1, theta 3, theta 4. Okay, you just 3, because our vision, the way we present things, we are limited to 3-dimensional space. Or you can plot it in another. We just project the values into a 4-dimensional space, from 4-dimensional space into 3-dimensional space. That's also possible. But normally, given no projections and no transformations, we just say in 3D space, it's hard to see, and so that's why we are going to take 3 at a time. Okay, but then what will happen if there are 4 joints? What will happen to the world space? The hand still moves in 3-dimensional space. It's still hand X, Y, and Z. No change. It doesn't matter how many joints move. The hand can only move in X1, X, Y, and Z. You understand? So you'll have like an arm, like a snake. Okay, so many joints, but still the head of the snake can just be in the 3-dimensional space of X, Y, and Z. When we're considering only the position of the hand. Okay. Any questions? So that I want you to really fully understand this part. I guess it should be easy to understand, especially when you do the exercise in the lab. Okay, and then now let me go to the inverse kinematics so that you can also do the second part of the lab. Okay, so this is forward kinematics. So the inverse kinematics, so in this case, the forward kinematics, we have input Q. You're saying Q is theta 1 and theta 2. So that was a question in the last meeting. So this is actually a vector of theta 1 and theta 2. Normally, Q are what we call a generalized coordinates. So that means that you just assign a value Q, then that means it's just the coordinates, theta 1, theta 2, theta 3, whatever. Or it could be also the link length will also change, but I don't want to concentrate on that because it will just somehow confuse you. Let's just concentrate on joints that are rotational joints, yeah, where the angles change. So given the angles that are changing, so you have the output that is X. In this case, this is also a vector, which means that this can also be composed of X, Y, and Z. At the moment, we only consider the position, so it will be 3-dimensional vector. Okay, so it should be like that. It's a vector, and that one is a vector. Okay, so if it is a single degree of freedom robot, then you only have theta 1, and then it will output HX and HY. If you have 2-dimensional robot, the input is theta 1 and theta 2. The output is HX and HY also. So if you have 3-dimensional robot, the same thing. Input theta 1, theta 2, and theta 3. Okay, but still the output is HX and HY. Okay, it doesn't matter how many joints you have, the hand position will still be HX and HY because this is a planar robot. Theta 2, theta 3, theta 4, how many? What will happen to that one? Well, it doesn't matter. Your hand will still move. So if you have 5 joints, your hand will still move with respect to HX and HY. So physically, what will it look like? Then you have, let's say you have a base robot like that. And then you have, let me just change the color. So this is your base, and you have your Maybe your joint 1 is here, your joint 2 is there, joint 3 is there, joint 4, joint 5 there, and then your hand still stays in the HX and HY coordinates, okay? You understand? Okay, I don't want to talk about redundancy now, but yeah, I just say that your hand will move in same world space, world coordinates, because you are moving with respect to the plane, and then it doesn't matter how many joints you have. Okay, well, you can have at least one joint, but then you can say that in this case here, if you have only one joint, the movement of the X and the Y is not independent of each other. Okay, they are constrained. Okay, so your HX and the HY goes together. Okay, they are not independent of each other because you're only moving one independent variable theta 1. Okay, but if you have two coordinate joints, so well, if it's like that, then you can say that you can control the HX and HY now, because you can choose not to move to a certain location in terms of X and Y. So how can you do that? So for example, well, you can do that. For example, okay, I'm just discussing about constraints now. So we are saying that in this case here, you have one joint angle. The movement of the X and Y are not independent of each other. When you move in X, you also move in Y, because you only have one joint coordinate, which is theta 1. But when you have theta 1 and theta 2, then your movement can be independent. Okay, so for example, you have theta 1 here, okay, and then maybe theta 2 is here. Okay, so that is your HX and HY. Okay, now I want to say that I want to move the X only, and the Y remains the same. Okay, so that means that I can choose, for example, to move here. Okay, to move here, this is the new point. Okay, where your Y remains the same. Okay, so how do you do that? Well, you change your joint. It could be like this. Okay, and then this one could be like that, or yeah, like that and like that. I mean, roughly speaking. Okay, so what I'm saying here is that in this case here, you are not just constrained in the two angles, because you have two independent variables, theta 1 and theta 2. Now your movement of the X and the Y direction are not constrained to be coupled to each other. They can move independent of each other. So two independent variables, theta 1 and theta 2, will result into independent movement of X and Y, HX and HY. But here you only have one independent variable, and so the movement of HX and HY are coupled. Okay, so but anyway, this is what I'm trying to say here, that the number of inputs will result into independent movements of the output if you have at least the number of inputs is at least greater than or equal to the number of outputs. Okay, then you have independent movements of the output. Oh, sorry, in this case, the number of outputs. Okay.
So can you go over it again? Can you go over it again? I think I missed something.
Which one?
What you're making right now? I think I missed.
Okay, the
some
number of
close line.
inputs must be greater than or equal to the number of outputs for independent movements so that the outputs can be independent of each other. I mean, that's the normal, because the inputs, okay, if you consider inputs, we assume that all inputs are independent of each other. So theta 1, theta 2, theta 3, they don't influence each other. Okay, we can move independently. So the X and Y coordinates can move independent of each other if your number of inputs is equal to or greater than, at least equal to or greater than the number of outputs. So in this case here, you have two outputs, HX and HY. So you need two joints to have the movement of H and XY, HX and HY to be independent of each other. If you only have one input, theta 1, then the movement of HX and HY cannot be independent of each other. Okay, they're coupled. Coupled meaning one will move and then the other will go with it. But here you have two joints. You can see that one will move HX, but HY you can choose to maintain it and not be influenced by the movement of HX, because you have two joints that can do that. You have two independent variables to have two independent input variables to result into two independent output components. So if you have three joints, definitely you have two, the movement of HX and HY are also independent. Three, at least two or more, then the movement of HX and HY are independent. Okay, I mean, that is normal for any systems. That is normal. So two independent variables will result into two independent outputs for any physical systems if they don't influence each other. Okay. Okay, so that's why as you increase the number of joints, well, the movement in HX and HY will become, I mean, independent, just like the at least two joints. Okay, I hope that that one is clear. So let's continue. So now we move now to the inverse kinematics topic. Okay, I want to slowly go here because this is something that I really want you to understand. Okay, and it's easier to understand in terms of the planar robot because we can imagine it. Okay, I want to finish this control part so that in the planar sense, so that you can now have an overview of what's going on, so that when we discuss in terms of the full space, then we always imagine back to the planar space, so that you can have a basis in terms of understanding, so that you'll have a stronger sense of understanding on how we move in terms of six-dimensional space, three-dimensional space and position, and three-dimensional space and orientation. That will be hard to imagine. But if we go back to the plane and we can do an analogy from the full space, six-dimensional space, into the planar space, then it will be better for you to understand. Okay, so I want to finish this whole discussion of forward kinematics and inverse kinematics in the planar sense, so that you can have a better understanding. Then we make things complicated, then you can still go back to this so that it will be your reference. Okay, so now we already mentioned that there is a computation of forward kinematics where you have inputs of the joints will result into output of the hand. Okay, input joint, output hand. Okay, so that means that we move the joint like that, we move the joint like this, then we can compute where your hand is. Okay, now we want to do the other way, because what we really want to have a meaningful movement in the world is that the hand, we command the hand to do somewhere, because that is where it will manipulate objects. So for example, if there is that hand, pick and place, it will place this object into the second location here, for example. Okay, so the question is, how will the robot move so that this object that it picks will be transferred to here? Okay, so that is what we want. We want to specify that to the robot. Then the robot will compute what are the joint values that it will need. Okay, so joint values it will need, for example, or maybe that's wrong. So maybe you will move here and you will move there. Okay, like that. So we
So I
don't.
have a question.
Yes.
Just to clarify for myself, the difference between forward kinematics and inverse kinematics is that in inverse kinematics, you are specifying the movement of the hand, while in forward kinematics, you are specifying the movement of the joints. Do I have that correct?
Exactly.
Okay, thank you, sir.
This is the part of, okay, this is the part of the forward kinematics where your input are the joints and the output are the hand movement. And this is the part of the inverse kinematics where your input are the hand movements and the output are the joints. Okay, so what happens here is that this output of the joints, it will be computed by the robot, by your computer, and then it will send as a command. Okay, later we will discuss that one, but for now we say that they have different inputs. Okay, the forward kinematics, the input is the joint, outputs the hand. The inverse kinematics is the other way around. Okay, and then how we proceed from there, from the computation, is that that is the next. I'm just discussing this, and then that is the next step. So how do we move from forward kinematics to inverse kinematics in a much easier way? Okay, there are other ways to do that. Okay, but the fastest way is to say that we have, okay, to say we take the derivative, we linearize the system, because in this case here, this is not linear. That is not a linear equation. Okay, the forward kinematics is not a linear equation, and so if you take the inverse of that, it will be difficult. Okay, there's no direct inverse to that. So but then when we linearize meaning, if we take the, in this case, I mentioned it already before, that if we take the derivative, okay, say with respect to time, derivative of x from your forward kinematics, x is equal to f of q. We take the derivative of x with respect to time, and also the derivative of f of q with respect to time. And because f is independent, because f is dependent of q, and so you have a second derivative. You take the derivative of the independent variable, partial of q with respect to partial of t. That's it. Okay, so when you take the derivative now, this is the derivative of the forward kinematics. This is what we call, it becomes a matrix. This is a Jacobian matrix. Okay, now you multiply it with the partial of q with respect to t. How the Jacobian is computed, we will discuss. Partial of x with respect to t. Now that becomes a linear equation. Okay, how do we say that an equation is linear? How do we say that the equation is linear? A set of equations is linear. Okay, well, okay, there are formal definitions of linearity of equation. For example, if x, or not x, how do we, the input variable, okay, never mind. Let's say y, okay, is equal to a0 plus a1 x1 plus a2 x2 plus a3 x3, like that, and so on. Okay, is this equation linear? Is that linear? Okay. Formally, a linear equation can only be zero if all the coefficients are zero. Okay, that's the formal definition of linearity. It cannot be zero unless all the coefficients are zero. Okay, well, of course, it can be zero. I mean, depending on what values, the result will be zero if all the inputs are zero. But if given that all the inputs are not zero, it cannot be zero unless all the coefficients are zero. Okay, that's one way of saying that the expression is a linear expression. Okay, things are not coupled, basically. Okay, the components are not coupled. It's like you don't have y is equal to a1 plus, or a0 plus a1 x1 x2, for example. Okay, so in this case, even if all your x1 and x2 is zero, okay, I mean, if your x1 is zero and x2 is not zero, I mean, and then it can only be zero if the coordinates, if all the coefficients are zero. Well, it's the same as this one, but in this case, they're coupled together. Okay, so in this case, they are not independent of each other, and so it is causing, this is not a linear expression. Okay, so in terms of matrix equation, okay, there are many ways to do that, but for us as engineers, I would say that we can say that things are linear if we say okay, a is equal okay, y can be equal to, or x a times b. Okay, like that. So it is linear if you can say that an expression of x equals a times b. If you can, all the matrices, I mean the terms and the vectors and the matrices can be expressed as x is equal to a times b, then that is linear, or b is equal to a times x, ax, like that. Okay, so in that case, okay, or I don't call it, or some matrix M times X. Okay, so in our sense, as long as we can express one vector against the other, and there is a matrix that multiplied that vector to get the resulting vector, then that's linear. Okay, and that is the case of this Jacobian matrix. Okay, where this is one vector and another vector, and the matrix, the Jacobian matrix, defines the relationship between the vector partial of q with respect partial of q with respect to partial of t against partial of x with respect to t. So in this case, that's linear. Okay, so now we say that it is a, what is the time now? Everything is it's 12 o'clock. So I want to stop here so that you can think about how the linearity of the matrices. So what I want you to understand is that the forward kinematics, x is equal to f of q. It's not linear because in our sense, you cannot express it in terms of coefficients. Separate coefficients, x independent variables, theta 1, theta 2, theta 3, with coefficients A1, A2, and A3 that are independent of each other. Okay, so in this case, it is not, we cannot write it in this sense. Is a polynomial linear? Yes, it is a polynomial. Is a polynomial function linear? Yes, it can be considered linear. Okay, even if you have a degree, for example, this one squared, okay, x cubed like that, and x to the n, it can be considered linear if, in this case here, all the variables are independent of each other, and they can only be zero once the coefficients of A1, A2, and A to the n is equal to 0. Okay. Okay. Maybe let's do a more formal definition of linearity when you come back. Okay, but for now, let's just so you can be reminded, and also I will be reminded of the formal definition of linearity. But for now, as long as you can write this as AX equals B or AMX is equal to B in matrix form, then it is linear. Okay, we'll come back. Let me pause the recording.